Today I'm going to be talking about some distribution-free prediction intervals. This is a project that myself, Dr. Dan Nettleton, and Dr. Dan Nordman have been working on for the past little bit. So without further ado, here we go. This slide is kind of a mixture of a couple slides that we've put together. We're going to talk a little bit about the background, very quick background for prediction intervals, talk about the new methodology itself, go into some case studies specifically applied to the sports realm, get into a little bit of simulation, and then talk a little bit about some future work. So for those who aren't familiar with prediction intervals, the idea behind a prediction interval is that we want to somehow provide information related to the uncertainty of point predictions. So if we're just giving a point prediction, that doesn't necessarily tell us everything we need to know. So we need to sort of bound these point predictions on one end or the other, or both, to kind of capture that uncertainty. Ideally, these prediction intervals provide a region where an observation will fall within that region with a specified probability or a specified amount of the time. So, if we think about a 90% prediction interval, for us, that means 90% of the points will fall within the prediction interval that we generate. So here we have just an example of what what a prediction interval might look like. Here we have a collection of point predictions, those black dots, and then the lines you see across those black dots are the prediction intervals. For this particular example, the red lines are where the prediction interval does not include the true outcome, and the black lines are where the prediction interval does include the true outcome. Some prediction interval methodologies that currently exist. A lot of you might have used normal prediction intervals, where we make an assumption that the error is distributed, normally distributed with mean 0 and some variance sigma squared. We might also use, if we want more of the distribution-free flavor, like we're talking about in this presentation, we might use bootstrap prediction intervals, which uses resampling techniques of residuals coming out of continually refitted models to get prediction intervals. We also might look at conformal prediction intervals, which have come out and kind of aggressively been used and are very effective and have finite sample validity for prediction intervals that only assumes exchangeability, which is pretty minimal assumptions to get valid prediction intervals. So the motivation for our new distribution-free prediction intervals, again, comes from a sports context. What we want to do effectively is, say we have an ongoing season for some sports competition, whether that be football, soccer, baseball, what have you. The idea is we want to attach some sort of prediction interval to the margin of victory for a certain game between two teams, say team A and team B. By margin of victory, we just mean the difference between the two teams' points. For sort of simplification, we say margin of victory might be home score minus away score. So for these sports competitions, the assumptions that we make that might making normality assumptions might not apply or might not be good assumptions to make for this particular sports competition. So what are some of the things we can do? And we'll get into what we can do, but we're going to build this motivation a little bit right now on this slide. So say we have a 4-team league, 4-team competition. What we want to do is predict the margin of victory for week 5 and attach prediction intervals for week 5. So at this point, the sports competition has gone on 4 weeks. We have 4 teams, and all of the teams have played each other for the most part. What we want to do is attach these prediction intervals. So what we propose is a method that sort of runs like this. We would fit a model using weeks 1 through 3, using what the home team is, what the away team is, and the margin of victory, try and fit a model with that information from weeks 1 to 3. We would then predict week 4 using the model fit from week 1 to week 3 and get a point prediction for week 4. Then we would take the actual outcome for week 4, the actual margin of victory, and generate residuals based on our prediction coming from the trained model using weeks 1 to 3. And we would find out how bad or how good we actually did at predicting those week 4 games that include team 2 playing team 4, team 3 playing team 1. So now at this point, for this example, we have sort of a collection of residuals. And in this case, we have 2 residuals, one for the game where team 2 plays team 4 and team 3 plays team 1. Now the idea to attach or to generate a prediction interval for week 5 is we would use the quantiles of our previous week's collection of residuals and use that as our sort of guideline or basis estimate for the true error distribution, or the true quantiles associated with our error distribution. And so with that, we can then find a point prediction for week 5, and then using those quantiles of our collection of residuals, attach prediction interval endpoints to our point prediction for week 5. And so as the season progresses, we can keep building this collection of residuals and keep providing more accurate prediction intervals as the season progresses. So in a sense, the general idea is that if as our competition increases, you can see we have 2 plots here that go from period 0 to period 50, I believe, or period 45. The idea is we can continue to create and generate prediction intervals as the season progresses using our increasing collection of out-of-sample residuals. So off to the left, we have an example where the true distribution, the true error distribution is normal. And so we can see that the normality assumption or normality-based prediction intervals seem to perform a little better from a coverage standpoint than our out-of-sample prediction intervals that we generate week to week. But if we, say, have a situation where the error distribution is not normal, which is a situation covered in the right plot, our prediction intervals perform better as far as getting closer to nominal coverage, whereas the prediction intervals generated using normality assumptions overcover pretty drastically. So that idea is we want to sort of take that out of the equation, as far as we don't necessarily need to make normality assumptions in order to get good prediction intervals or get tractable prediction intervals even. So we're going to go into the methodology a little bit. So in order to do that, I'm going to talk about some notation. So YIK is the response for the ith observation in period K. So when we talk about period K, that goes back to our sports example where period K might be period 5, and then we would go period 6, period 7, period 8, where in the sports context, it's kind of already broken up into a weekly sort of competition. Y hat IK is the predicted response for the ith observation in period K. XIK is a vector covariates associated with the ith observation in period K. XK is the matrix of those covariates through time period K. So it's a matrix that includes all of these vectors of covariates for all games up to and including period K. This beta hat K is a collection of, or a vector of parameter estimates generated using all the information up to period K. NK is the number of observations through period K, and then we define N as just N capital K, which is the number of observation in our total number of periods, where our total number of periods is K, capital K, excuse me. MK is the number of observations in period K, so we can sort of classify NK in terms of the sum of all of these individual MJ values. We also have this sigma hat K, which is an estimate of our expectation X transpose X matrix. So this is a matrix estimate that we use and have to sort of make assumptions about in order to get these, to show that these prediction intervals are valid. RIK is kind of what guides the prediction intervals. We generate these out-of-sample residuals by fitting a model from a certain number of periods and then predicting and getting residuals for observations not in the periods we created the model with. And then QK tau is just the quantiles associated with this collection of out-of-sample residuals, where QK tau is the tau quantile for all of those residuals collected up to and including period K. So with this notation, we can kind of get into the assumptions that we're currently using to show that these are valid prediction intervals, or that we can generate valid prediction intervals. We assume some linear model where yik can be described by x transpose ik beta, where beta is the true set of parameters. And then we have some error component, epsilon ik, as well. And then we also assume consistency of our beta hat k estimates as far as beta hat k approaches in probability to beta, and then our epsilon hat k approaches in probability to epsilon, where epsilon is defined as the limit as k goes to infinity of the expectation of xk transpose xk over nk. And I'm sorry I didn't have that in the slide. That was I should add that the next time I present this. We also make assumptions about epsilon itself, the error component, that each error component, epsilon ik, is IID from f, the distribution function for the errors, and we assume that's continuous. We also make an assumption that our vector of covariates, each xik, are tight. The final assumption is that there exists a subsequence L that's less than K, such that L goes to infinity, K goes to infinity, and L goes to infinity, and NL over NK goes to 0. So this is just attempting to get at sort of, there are certain pieces of our estimates that don't necessarily follow these assumptions laid out, but if the number of observations that don't follow these assumptions is small compared to the total number of observations, then we can effectively throw out those observations that don't follow these assumptions. And as long as that is small compared to our, K number of observations in our K periods, then we're good to go. So we kind of got an idea of how to build these prediction intervals, but we'll lay out the methodology steps again. So first, we're going to fit a model, and we'll call that model AK, where AK is a model fit using all of the information up to period K, up to and including period K, excuse me. We identify that K starts out to be K naught because we just want to eliminate any estimability issues that might come later on. So this K naught is just chosen that we eliminate those estimability issues. So that means we would start, in the sports context, we would start at the 3rd week or the 4th week of the competition instead of using the information from week 1. We then take this model, AK, and we generate out-of-sample residuals using AK and our sort of next week's observations, or excuse me, the current week's observations. So we know the outcome for all of the observations in week K. We predict them, and then we get our out-of-sample residuals when we compare them to the actual observed observed response. We then take those out-of-sample residuals and we use quantiles of those modified out-of-sample residuals and a new model AK plus 1. So this AK plus 1 is a model fit using all of the information up to and including period K plus 1. So we use quantiles of residuals generated through period K, and then we predict with a new model that we build off the current week's observations and everything prior to that. And then as we progress, we keep repeating all of this until we effectively exhaust our number of periods. And by that, we mean until we've reached effectively the end of the data set, or the end, in the sports context, the end of the competition. And we can continue to grow this. There are potential adjustments that can be made that can probably enhance these prediction intervals as far as get them closer to the true prediction intervals, but we haven't really explored specifics of that yet. And when we say modified out-of-sample residuals, I've kind of been throwing this term around, but we define this as yik, so the true observed response for observation I from period k, minus our predicted response from from observation I in period k. So keep in mind that the prediction y hat ik comes from a model fit, in this case, a model fit using information from periods 1 to k minus 1. And then we effectively divide by our residual variance. So we have this sort of 1 plus square root of 1 plus our hat entry for our new point. And that's what we use, that's what we take the quantiles of to get our prediction intervals. And we kind of outline this in this slide here, as we take our prediction for a specific period k, observation I in period k, we add a quantile of our modified out of sample residuals, and then we scale it back by the square root of 1 plus the hat entry for our new observation, And these are equal tail, so, but because our modified out of sample residuals aren't necessarily symmetric, we can see that we don't have the same quantile value necessarily, a negative version of the quantile on each side as we would potentially for, or as we would definitely for a normal prediction interval. So we have qk minus 1 alpha over 2 quantile, and qk minus 1 minus alpha over 2 quantile. And that's how we generate our prediction intervals. So there's more mechanics to this, but basically what we found is that when we define some empirical cumulative distribution function that takes into account the periods and the residuals from which those periods come from, or the periods from which those residuals come from, we can define it and we can make something that actually is a valid estimate of the true empirical distribution function f of our error distribution, of our error values. And that means we can just use them to generate asymptotically valid prediction intervals. Excuse me. As long as we stick to this definition, defining this inverse function, and then also going with the previous assumptions that we outlined in a couple slides earlier. So like I said, this allows us to provide these asymptotically valid prediction intervals using our estimate of the empirical CDF function up to period k. We can also use this estimate for event probabilities. So instead of doing prediction intervals, we can talk about estimating a probability that an observed response is greater than 0, instead of bounding it on both sides in a prediction interval. Sorry. So because the motivation for this method kind of came from a sports context that has sort of this temporal aspect where the data grows in, week by week or game by game, a lot of our case studies have to do with application to this sports context. So a lot of the things that we've done related to sports is talk about win probabilities related to the National Football League, WNBA, English Premier League, and NCAA basketball. So I'm going to go through a couple of those case studies specifically, National Football League and NCAA basketball. So in the sports context, it kind of lends itself to a specific model that sort of is most effective. And the model that we've been using in the sports context is just a simple linear model, specifically called the Harville Method. So the Harville Method is effectively a ranking methodology. It applies a linear model to predict margin of victory. And we have margin of victory, again, defined as the observed margin of victory for Team Q playing against Team R is just the home score, where Team Q at this point would be at home and Team R would be away. And we just subtract the two, home score minus away score, to get margin of victory. But it's just a simple linear model that when we fit it, we actually get effectively team strengths associated for each team. And that when we use those, we can actually compare and then use it as a predictive model to generate predictions for the upcoming week's margin of victory based on who is playing who in the next week. So here we also identify a home field parameter. We have the strengths of team Q and team R as SQ and SR. We have our error term for team Q and team R. And then we fit a model to get estimates of the home field advantage parameter and then the respective team strengths. So this is the model we use for all of these sports-related case studies. So behind all of this, behind all of the generating of this, the Harville method is kind of the key, the model that we use. But when we talk about prediction intervals specifically for our case studies, we want to know, hey, how good are these prediction intervals? And that kind of lends itself to two things: is how long are the prediction intervals and how well do they cover? How good is their coverage compared to nominal? So here this slide talks about, or kind of shows how well our prediction intervals cover when compared to nominal. So we took all of the regular season data for all NFL games from 2010 to 2018. We were originally doing this, the 2019 season was kind of midway at its midpoint, so we didn't quite complete. But we can look at how decent the coverage is for all the respective years that we looked at for the NFL. So when we're looking at saying nominal, or when we see that nominal is 90%, we can see that we do okay as far as meeting, for the most part, meeting that nominal. We're a little bit under coverage for the most part, and you can see in 2015, 2017, we get a little bit lower than what we might like, but these prediction intervals seem to be doing well at identifying prediction interval endpoints that meet nominal coverage, or at least get close to nominal coverage. When we talk about the idea of event probabilities or win probabilities in a sports context, we also want our win probabilities to be calibrated. And by that, we mean that when I say that a team has a 60% chance of winning, the number of times I say that, the team should actually win 60% of the time. So this is reflective of how good the estimate for the cumulative distribution function is. So if we look at it, we should kind of fall along the dotted line on the diagonal. And for the most part, we seem to do okay as far as getting close to that dotted line. You can see kind of off to the right at about the 0.8 region, we kind of drift off the diagonal, and the same thing kind of goes with on the left side, or the lower portion of the plot. All those points are related to low sample sizes in these collections of points, or that are averaged with each of these points. So not so much of an issue, but for the most part, we seem to do well at providing calibrated probabilities specifically for win probability in an NFL context. Another thing that we tried to do, again, talking about win probabilities or these event probabilities, is we sort of wanted to talk about NCAA. So a lot of us, a lot of the issues that are coming, there are a lot of issues that have come from this COVID-19 pandemic. One of those being that all of, professional sports were kind of put on hold until actually very recently. Also, the NCAA tournament for both men and women were canceled for 2020. So in order to sort of fill that hole that was left by the cancellation, we wanted to look at who do we think actually was going to win these tournaments. So we looked at and tried to simulate the entirety of both the men and women's 2020 NCAA tournaments. So we utilized regular season results to kind of rank teams. We simulated the rest of the conference tournaments. So at the point where the NCAA tournament was canceled, a lot of the conference tournaments had already been completed, but there were still, I think, 18 conference tournaments remaining for the men and 19 for the women. So we simulated all of those conference tournaments starting from where they had been canceled. So at some point, the cancellation kind of cut off right at the end or right in the middle of tournaments. So, at one point, I don't remember what conference it was, but there was the final game was just left and it got canceled. So there was two teams that would have played for a spot in the NCAA tournament and it got canceled. So we finish from where these tournaments got canceled, get the winners to talk about, hey, who automatically got a bid into the NCAA tournament, and then who was an at-large bid. We also seed these teams based on the team strengths that we generated using the Harville Method and the regular season data. And then we also, I don't think I have it in this slide, but we also compare our bracket results and our simulation results to what might have happened with an alternate bracket. So a lot of subject matter experts in basketball released their own bracket prior to cancellation to kind of give their idea about, yeah, we think these teams are going to be at this point in the bracket and who's going to play who. So we also use those subject matter expertise generated brackets and kind of compare what team might have done better in what bracket. And just for clarity's sake, we did this 100,000 times. So effectively estimated or simulated the entirety of the remainder of the conference tournaments and March Madness 100,000 times. So I'm going to give a couple results for those. Off to the left, we have the men's simulation results, and off to the right, we have the women's simulation results. So for the men, Kansas seemed to have the highest probability of winning the tournament at about, looks like 26% chance. So that means in all of the NCAA tournament simulations that we executed, Kansas won the tournament 26% of the time. Gonzaga in close second. I don't know if that's actually close, but in second place nonetheless with a 15% chance. And then another one I have pointed out for the men's is Dayton. My wife is actually from Dayton, so it was the best season they had to date. They were ranked third in the country, and it got canceled. So it was a sad day in our household when that happened. But Dayton seemed to be a little overranked, I would say, because they are definitely have lower probabilities than a few other teams that weren't reflected in their overall rankings from like an AP poll perspective or a coaches poll perspective. Up to the right, we have the women's results. So UConn, storied program in women's basketball, had about, again, a 25% chance to win the tournament, followed by South Carolina and Princeton. Princeton was kind of an interesting team because a lot of subject matter experts had Princeton not as highly ranked because they played in the Ivy League, which is assumed to be a weaker conference. So it's kind of interesting to see how different the ranks are when you take into account the leagues that the conferences that these teams play in. And I have some other slides in background if anyone's more interested in results that are coming from this NCAA simulation or NCAA case study. So additional to these case studies, we also looked at a simulated example. And this simulated example, we sort of mimicked how a competition might play out, but we extend the competition length to a longer period. So instead of, for example, football, instead of teams playing for 17 weeks or playing 16 out of a 17-week season, we extend that to a 50-week season just to see how well the prediction intervals perform further on in time. So we kind of fix a set of teams and these team strengths. We generate this extremely long season. We capture our prediction interval coverage at a weekly time point, each week. And then we also repeat this process for each week. So we get kind of an averaged estimate for the coverage for each week. And so we have two examples. Off to the left is where we have 12 teams in a league and we have a 50-game season. And off to the right is we have 500 teams in the league. So you can see that we definitely perform better. Our estimates, our prediction intervals definitely have better coverage and tighter coverage around nominal the more teams we have, whereas compared to, say, a 12-team league, we still seem to be centered around our nominal coverage of 90%, but it's definitely more varied. And we, again, this probably should have been after the NCAA tournament, but we also wanted to look at, hey, how well did these prediction intervals that we generate using our modified out-of-sample residuals, how do those compare to a normality-based prediction interval? And this is the calibration plot, similar to the NFL calibration plot that was shown, that tries to identify, how well these prediction intervals are calibrated. And you can see they seem to be very similar, but off to the right and off to the left, the out-of-sample prediction intervals perform much better than the normality-based prediction intervals specific to the 2015 to 2019 NCAA basketball seasons. And just to clarify, these are the 2015 to 2019 men's regular season. The women's regular season was a lot harder to find, so we only had, at that point, the men's data from 2015 to 2019. So we do seem to be performing a little better than normality, which is promising when delivering a new methodology. So the way that we build these residuals, we break it up into for example, K periods across an entire season of sports, if we stick to the sports context. But there's no reason why we couldn't say, okay, if I have n observations in my data, there's no reason to say that we can't have n periods. What that means is effectively every new observation, we are fitting a new model and generating a new residual, a new out-of-sample residual, and we're doing this every observation. So we effectively have a new model built every observation and new prediction interval quantiles every observation. So this is a special case of what we kind of talked about earlier, this sort of K period based method. We also, and we haven't finalized the proof or formalized the proof about this yet, but we've talked about a leave D out residual generation. And what that means is kind of a cross-validated approach to delivering these prediction intervals. So instead of one model fit across K periods, we say, okay, during period K, I want to continue to have K periods, but I will fit K different models. And each time I'm leaving a different chunk. Effectively, I'm leaving D different observations out to generate K models, and we get a larger set of modified out-of-sample residuals every K periods. And that seems to be effective in, again, getting better estimates of our empirical cumulative distribution function and getting better prediction intervals from a coverage perspective. So we've talked about the sports application, which for us has been sort of a side-by-side comparison. This team versus this team, who has the better margin of victory for each observation, and what is that margin of victory? So using that same sort of archetype for how we can apply this, a previous presentation dealt with street safety in Chicago with this data set, this place pulse data set. So we could do something similar to the sports context, where we have this data set that talks about whether image A or image B is more safe or more unique. I think in the data set itself, there's 4 or 5 different identifiers about when they get information, what they want the end user or what they want the person rating these images to rate them on. So we could do something related to providing prediction intervals of the attractiveness of an image or probabilities associated with whether or not a certain location based on images of it would be more attractive from a safety perspective or a uniqueness perspective, whatever else is in the data set. So this is just an alternate application. We haven't done anything with this quite yet, but it seems to be within the wheelhouse as far as the current methodology is concerned. For future work, we'd like to talk about what are the rates of convergence for our out-of-sample empirical cumulative distribution functions, how good are these prediction intervals, and we'd like to continue to compare them to other distribution-free prediction interval methodologies. So we've already compared them sort of to the normality-based prediction intervals. We'd love to compare them again to conformal and bootstrap prediction intervals. And something that's come up recently is leave one out prediction intervals or jackknife residuals. Can we use those, or can we compare them to, can we compare our methodology to prediction intervals generated using jackknife residuals? So that's all on the forefront. And our references. So without pending any further questions, that concludes my presentation.
Okay, so time for a few questions.
Can I ask a question?
Yes.
Yeah, this is Zhenyuan Zhu from Statistics. Thanks for presentation, really great work. Could you just go back to the slides where you show the NFL prediction over the last maybe 10 years? Yeah, this one. So it looks like you got it pretty close to 0.9, but 8 out of 8 times, or 9 out of 9 times, 8 out of 9 times is less than 90%. Mm-hmm. It seems to me that suggests some a slight under coverage, and I think that there's a if you are doing this for NBA, I would think that you probably have a slightly larger under coverage, because if you look at your assumption, you assume the model is correct, right, when you're going forward. But in the sports, like I don't know about NFL, but I watch NBA a lot, and when there's a starter got injured, then your probability of winning a game reduced a lot, and that will become kind of out of the prediction bound in your case. And can this be taken into account? Since I think the good thing about the sports is that you have a huge amount of historical data from the previous, let's say if you're looking at 2007, the first 2008, the first 8 years. Could you use that to come up with some kind of correction to make that coverage unbiased?
That's a great observation. Thank you for that. So yeah, I agree that there is definite undercoverage or evidence of undercoverage, and there's a couple things, and you've also identified another issue with the current model set is, yeah, we don't sort of take into account how well a team or how a team changes. So, you know, if an individual that, you know, provides some star power to a team is out of commission for due to injury or whatever, that we don't necessarily identify that and can't respond to that with the current model. So one thing to address that might be to, instead of using all the way from period, you know, the beginning of our data to period K, we sort of shorten the window so that we are effectively eliminating, you know, or kind of weighting less the observations that are too far out of the current strength of the team. Additionally, instead of continuing to hold all our residuals from the start all the way to when we finished our data, we could also drop out residuals. And that kind of goes to assumption 6, is that we sort of see that, you know, for some parts of the model, we might not follow assumptions, but as long as those number of observations are small with respect to our total number of observations, we're okay. But if we just actually drop those residuals out that might be a result of broken assumptions, then it might also positively affect this under coverage issue. Yeah, and I think you're right. As far as WNBA is concerned, we haven't looked at NBA, but as far as WNBA is concerned, the under coverage is a little bit more apparent with WNBA. So I don't know if that translates to NBA as well, but from a basketball standpoint, you are correct in that there's a little bit more under coverage with basketball as opposed to football. Did I answer, or did I talk to every part of your question? I'm sorry if I missed something.
Yeah, that's a great answer. I'm just wondering if you could use historical data
Oh, yes.
To basically make some bias correction?
Yeah, so we've talked about that, and that is sort of a potential problem with this is this sort of cold start that happens when we want to generate these prediction intervals, is that the first week we do it, we're using less observations, and so we do have that bias associated with, or the bias that potentially comes, a larger bias that potentially comes with low sample size. So there are things that we've looked at, or there are things that exist that sort of would potentially alleviate this cold start problem. Some Bayesian methods. So I think that's definitely an option as far as eliminating this bias, and I think it could work. We just haven't emphasized trying to explore those options in this current context.
Okay, thanks.
No problem.
Any other questions? Okay, looks like we do not have any other questions. Okay, so let's thank the speaker. Thank you, Chance, for the nice talk.
Yeah, thank you so much for letting me talk for 40 minutes. I really appreciate the opportunity.
Okay, thank you. It was a nice talk. Yep. Okay, thanks everyone for joining us today. Yep. We'll see you next week.